So now that we know the pattern, how do we solve what I playfully call a hidden quadratic? And what I have is basically a step-by-step process on how we're going to do it. But overall, the idea, if you kind of think of this in terms of worlds, right? Right now, these equations that we have that are not quadratic, right? They're over here, dare I say, in our x world, right? And I want to basically try to find the values, right? What numbers that can I throw in here and make the equation true? What we're going to do with a substitution is we're going to transfer the problem to what I would call the A world. That's going to be the variable that I commonly use, but you can use whatever you want. And we're actually going to solve it over here in the A world because it's going to be a quadratic. So we're going from a non-quadratic situation in the X world to a quadratic situation in the A world. We solve it here, and then we're basically going to walk it back. Right? So we're going to be bouncing back. This is a very, very famous mathematical trick, and as you guys go on through your math careers, you're going to see it quite frequently. When we take something that is hard in the situation that I'm in, a substitution makes it easy, and then we basically map ourselves back to the solution in the world that we're in. So here's how this is going to work. The first step is to actually recognize that it's a quadratic, which we've done, and you're going to take the middle part and you're going to let it be another variable. So we've already established the fact that that middle term, when I square it, I get the first term. So I'm going to let a equal the x squared. So you literally label the variable part. Just to check, if I was to square both sides, right, I can see that x squared is x to the fourth. All right, so that's step one, right? Label a variable, usually with another variable, for the middle part. You're going to substitute. So x to the fourth is now a squared, right, because of that substitution, minus 17. X squared, right, is now a, and then plus 16 equals 0. So kind of like I did in my schematic, we're solving an equation that's not quadratic in the x world, but because of my substitution here, I now am sitting over here in the a world, and as far as a is concerned, this is a quadratic, right? So how do we solve a quadratic? Well, to make our life simple here, right? Everything should factor, right, pretty nicely because I want to concentrate on the substitution idea. And so if we use factoring, right, a minus 16, a minus 1 results in that quadratic. So the zero factor property now comes into play, meaning that a minus 16 is equal to 0. Or a minus 1 is equal to 0, adding some stuff to both sides, right, we get our two solutions. Now, what we have to remember is that these two solutions are sitting over here in the a world, right? As far as a is concerned, the solutions to this equation are 16 and 1. But we want to solve for x, right? That was the original variable. So we got to walk this story back. So I'm going to use my substitution combined with what I have here. So I have already found that a is 16. So we also know that a, by my substitution, is x squared. So this means that x squared is 16, or if a is equal to 1, that means that x squared is equal to 1. And so what we end up getting, right, to solve for x now, I'll use my square root property, right, in both cases actually, and voila, we get our solutions. X is plus or minus 4, or x is plus or minus 1. And so there's basically our solutions there. So you can kind of see that strategy where step one is to label my middle part with a variable, make sure that it is the quadratic that we're hunting for, substitute your x variables with your new variable, solve it using the quadratic things we've done, and then you walk the story back, right? So if a is 16 and if a is x squared, that means x squared is equal to 16. If a is equal to 1 and a is equal to x squared, that means that x squared is equal to 1. And then you basically solve it for x using things that we've learned in the past. In this case, I use the square root property. The last step is to check, all right? But I'm going to take advantage of the fact that since my math is good, I'm going to trust myself. And since this is a polynomial whose domain is everything, I'm pretty confident that these answers are going to work, all right? So I'm not going to bother to check it. That's going to be different down here because we already know because of the square root, right, our domain is actually limited from 0 to infinity. So the possibility of having extraneous solutions is probably going to rear its ugly head. But this is how it's going to look for this next one, right? So step 1 is to let your variable equal to let your new variable equal to the variable that's in the middle piece. And then just to make sure, if I square both sides, I find that a squared is equal to x. So everything looks like it's in order. So I'm now going to go to step 2, which is to substitute my new variable into the equation. So x becomes a squared. We now, by my substitution, I said the square root of x is equal to a, minus 40 is equal to 0. And just as promised, as far as a is concerned, this is quadratic. So how do we solve a quadratic? Well, there's lots of ways to do it, but I told you guys to make things simple. I'm going to make things nice and factorable right now. So two things that multiply up to negative 40 but add up to 3, right? I believe that's going to be plus 8 and minus 5. Right? Let's just check that. A squared, 8a, negative 5a is 3a, and then 8 times negative 5 is negative 4. Right? So the zero factor property says that a is equal to 8, or a minus 5 is equal to 0. Sorry about that. Subtracting both sides, adding both sides, we get two potential answers at the moment. Right? A is equal to negative 8, or a is equal to 5. Right? And so we got to walk our story back, because as I mentioned, right now we've solved our quadratic in the a world, but we actually want to solve things in the x world. So walking my story back, if a is equal to negative 8 and a is equal to the square root of x, putting these two together, that means the square root of x is equal to negative 8. Or vice versa, if a is equal to 5 and a is equal to the square root of x, that means that the square root of x is equal to 5. So how do I solve for the square root of x? Well, in both cases, right, to get rid of that square root, I'll square both sides. So we end up with x equals 64 or x equals 25. All right, so we have to be careful here, because we have because of our restricted domains, do both of these actually work? So I'll check them out. So if I check 64 plus 3 times the square root of 64 minus 40, this will give us 64 plus 3 times 8 minus 40, which is 64 plus 24 minus 40, right? We're trying to see if this equals 0, right? And I can see it's not going to, because this is already 88 minus 40. That's not equal to 0. So that guy is extraneous. What about this dude? If we substitute it in, 25 plus 3 times the square root of 25 minus 40, does that equal 0? Well, this is 25 times 3 times 5. 3 times 5 is 15, and 40 minus 40, 0 equals 0. So that is our solution, because it actually checks out. All right, and that was because of the domain restriction. We have to be very careful about what solutions come up, like we saw way back. I think it was in chapter 10. Alrighty, so there's basically your hidden ball trick, or what I call the hidden quadratic trick. The idea is we're trying to solve an equation that's not quadratic in the variable that we're beginning with. But I make a substitution, I plug that in, it now becomes a quadratic in the variable that I'm looking for. I solve it using quadratic things, right? And then I walk the story back, right? So in this case, a was x squared and a was 16, bring them together, x squared 16, and then we solve for x. Down here, right, my substituted variable is a little bit different. So if a is equal to, let's say, 5, and a is also equal to the square root of x, I make that walk back, right? That means that the square root of x equals 5, solve for x, and I end up with my solution. And you also saw step 5 in play, where you have to check to make sure that things work. All right, so there's our first foray, if you would, into solving hidden quadratics using what I playfully call the hidden ball trick, or the hidden quadratic trick of substitution. Right, so let's practice this. We've got 4 more equations that we saw from our groundwork. Let's go see how we solve them using this trick in some other videos coming soon.